Well, officially, hello everybody. Welcome back to lesson 7 on our introduction to physics. Happy Wednesday. So a quick overview for today. We're going to finish up chapter 2. So just quickly go through this example that we did together yesterday at the very end of class. I'll go through some of the chapter review questions with you guys so that you know what the most important kind of key concepts are from chapter 2, and then we'll jump on into chapter 3 and do some beginning of chapter 3 stuff today. So this is the example that we left off with yesterday. And remember, we were ending up talking about integrals, or the area under the curve. So remember, these three types of graphs that we've been talking about: position time, velocity time, and acceleration time graphs, those are all related to each other. So you can go from top to bottom in our stack of graphs, so from position to velocity, velocity to acceleration, taking the slope or the derivative, or you can go up the stack of graphs from acceleration to velocity, velocity to displacement, by taking the integral or the area under the curve. And remember, in these cases, under the curve means between the graph line and that x-axis. So we went through this example. What is the total displacement of the object over 18 seconds? If we recognize that this is a velocity time graph, that means the displacement is the area under this curve. So we take this area that has a negative height, so it'll be a negative area because, again, that's totally acceptable for this. And then we add it to this positive area. And I went through two different ways to do it. The first way is by breaking it down into two trapezoids, in which case we have an area of negative 60 and an area of positive 144, and add those together to get a total area or total displacement of positive 84 meters. You could also break it down a different way into rectangles and triangles, but we end up with the same result. Positive 84 meters is our displacement. So now, really quickly, as a review, I want you to think about how to describe in words what this object is doing. So take a quick minute, think about that. Remember, you're looking at a velocity time graph, not a position time graph. So how can we get information about what this object is doing from this graph? Take a moment and think. All right, so I know that was probably a quick moment, but let's go through a potential answer. So we know at the beginning of this graph, the object has a negative velocity, negative 12 specifically. So it could either be moving backwards or west or down, whatever our negative direction is, at a constant 12 meters per second for 4 seconds. And then we notice that the velocity decreases in magnitude to 0. Right, so that means it's slowing down to a stop. So right at 6 seconds, it is momentarily stopped. Its velocity is momentarily 0. Then we can see its velocity is increasing all the way up to 18 meters per second at 9 seconds. So what might be happening here is that it is changing direction, right? Then from 9 to 13 seconds, it's traveling a constant 18 meters per second east or forward or up, whatever your positive direction is. And then we see the velocity decreases back to 0 at 18 seconds. So it slows down to a stop. Okay, so if you think about like what kind of object is doing this motion, you could have a whole bunch of potential answers for this. But that's just going to help us think through what is sort of going on in this scenario. Okay, so here are the chapter review questions. Um, I'll leave it up to you guys. Do you guys want to think through some of these questions now and go through these answers? Or do you want me to just leave this slide in the notes? The next slide is the answers so that you have access to them on Canvas, and we'll continue moving on. Let me know in the chat what you guys would like to do. Do you want to go through them now or on your own? Okay, so what I want you to do then, since we have 3 votes for now, is to just take a couple of minutes, maybe 2 to 3 minutes. It's going to seem very fast, but take a couple of minutes, think through these questions on your own, maybe jot down the answers that you come up with, and then we'll go through the actual answers together once you've had time to sort of think through these review questions yourself. So we'll come back together in a minute or two. All right, so that might have been too quick for you to answer all of the questions, but hopefully that was enough time for you to start thinking through at least some of them. We'll go through the answers together, but again, this will be posted on Canvas. So later on, if you want to go back, take your time, really work through the questions yourself, then they will be available for you. And keep in mind too, that with these chapter review questions, these questions are taken from the chapter review in the textbook, which is where homework questions and quiz questions are also often taken from. So these would be pretty typical of the homework questions or quiz questions that you might see in Physics 1. So question 1, can an object with constant acceleration reverse its direction of travel? Yes, it absolutely can. For example, a ball thrown up in the air. The acceleration in that case is the acceleration due to gravity, which is always pointing down towards the center of the earth. And that's a constant acceleration for our purposes. It's not all, I mean, for our purposes, it's constant. But if you think about what the ball is doing, it's traveling up and then coming back down. So as it's going up, it's slowing down and then it speeds up as it falls back down. The acceleration is always the same, but it's reversing its direction of travel. Number 2, is it possible for an object to be slowing down while its acceleration is increasing in magnitude? Yes. That would be, for example, pushing the brakes in your car. You're traveling forward. Once you start pushing the brakes, your acceleration is backwards. It's slowing you down. So the more you push on the brakes, the bigger that acceleration or deceleration is. But that makes you slow down because your velocity and the acceleration are in opposite directions. That makes you slow down. So is it possible then to be speeding up while the acceleration is decreasing? Yes, that would be releasing the gas pedal. So kind of the flip side of that scenario. Under what conditions does the magnitude of average velocity equal the average speed? Always. Speed is the size of the velocity. Remember, velocity takes into account the direction, but if we're just trying to consider the magnitude of the velocity, then that equals the speed. Number 4, can you have a zero displacement and a non-zero average velocity? No, you cannot. Remember, the way that we calculate average velocity is displacement divided by total time. So if your displacement is 0, no matter what your total time is, you're going to have an average velocity of 0. Number 5, can you have zero velocity and non-zero average acceleration? Yes, that would be like the example in number 1, right? So our average acceleration for this ball being thrown up into the air and coming back down, the average acceleration is always down towards the center of the earth. That's the acceleration due to gravity. And at the moment the ball reaches its peak and is about to start coming back down, It is momentarily stopped. The velocity is going from positive to negative. And if you think about a number line in your head, for example, in order to go from the positive side of the number line to the negative side of the number line, you have to pass through zero. So whenever something is changing direction, it will be momentarily stopped right as it changes direction at that instant. But the acceleration does not need to be zero. Number 6, a car is traveling west. Can it have a velocity toward the west and at the same time have an acceleration toward the east? Under what circumstances? Yes, absolutely, this can happen. And that would be when it's slowing down as it's traveling to the west. Remember, velocity and acceleration, if they're pointed in opposite directions, your object will slow down. If they're pointed in the same direction, your object will speed up. And then number 7, a truck is at position 1 equals 277 meters at time 1 of 16 seconds, and at position 2 of 19 meters at time 2 of 25 seconds. Sketch 2 different possible position time graphs for the motion of this truck. There are infinite number of graphs that you could draw for this, as long as the starting and ending points are 277 and 19, and then at a time of 16 and 25. As long as those two endpoints are there, you could have any number of crazy things in between those 2 points. So based on those infinite possibility of graphs, is the average velocity between these 2 points the same on both graphs? Why not? Yes, your average velocity will be the same no matter how you drew your graphs, because average velocity takes into account just where it started and where it ends up. And that's going to be the same on any of your graphs, right? It's just the displacement divided by the total time interval. And those endpoints are fixed. But part C, is the instantaneous velocity between these points the same on both graphs? Why not? No, the instantaneous velocity will not be the same. That depends on the shape of your graph, right? Remember, the instantaneous velocity is the slope of the tangent line at any particular instant. So if you had a straight line connecting those 2 points, you would have this particular slope the whole time. That would be your particular instantaneous velocity. If you had a curve, then your instantaneous velocity would be positive and then zero and then negative. Sorry, I have hiccups. So your instantaneous velocity depends on the shape of the graph, but your average velocity does not. Okay. Hopefully those questions made some sense to you now that we went through those answers. Hopefully it made sense to you before we went through the answers together. But do you guys have any questions about chapter 2 before we move into chapter 3? Okie dokie. Well, if you do come up with questions, of course, feel free to stop and ask, or stick around after class, and I would be happy to talk through those with you. Let me go ahead and move into my chapter 3 PowerPoint. There you are. Okay, can you guys all see my chapter? Well, it says chapter 2 and 3 PowerPoint. Yes, great, awesome. Okay. So chapter 2, remember, was all about motion in one dimension. And now we're going to extend those ideas that we just covered into motion in 1, 2, or 3 dimensions. So let's take a look. Remember, yesterday we talked about some of our rules with derivatives, how to apply the power rule, the sum, difference, product, quotient, and higher order derivative rules. So we're going to put some of those into practice today to show you how we come up with all of these equations that we're going to use. And I will say, projectile motion, which is motion in 2 or 3 dimensions, does tend to be math heavy because there's a lot to consider when you're throwing things or people off of buildings. I mean, hopefully you don't throw people off of buildings, but I don't know your life. So we're going to show you how we get to some of these equations, and then hopefully that will help you connect these concepts together. Okay, so we're going to start here with this function, x equals, and we have 2 Greek letters in here, beta t plus 1/2 gamma t squared. Right now, those are just placeholders, and we'll figure out what beta and gamma mean as we go through this. But we're starting here with this position. Remember, x is position. So this position function. Well, if we remember from the past couple of days, taking the derivative of a position function gives us a velocity. So the derivative of our function x with respect to the variable time is the definition of velocity. And so when we take the derivative of this function, remember, apply that power rule that we talked about yesterday, we get beta plus gamma t. So remember, in the power rule, we multiply the coefficient by the exponent. So in this case, the exponent here is 1. So 1 times beta. And then we subtract 1 from the exponent. So t to the 1 minus 1 is t to the 0, which is 1. So we get just beta. In this chunk here, we do the same thing. Multiply the coefficient 1/2 by the exponent 2. That gives us 1. Gamma is treated as a constant because we're taking the derivative with respect to t, not gamma. And then subtract 1 from the exponent. So 2 minus 1 is 1. So gamma times t is our first derivative. That's the equation for velocity. Okay, cool. But we still have beta and gamma in our equation, so not super helpful yet. It will be soon. Let's take the second derivative now. So remember, the derivative of a derivative, we go about it the same way we do the first derivative. But when we take the derivative of a velocity, that's like taking the slope of a velocity graph, that gives us an acceleration. So the change in velocity over time is the definition of acceleration. And when we take the derivative of this, beta goes away because that's just a constant. There's no t associated with it anymore. And so we just get gamma as our acceleration. Well, that means that anywhere we see this variable gamma in our equation, we can replace it with the variable a for acceleration. So in our first derivative equation for velocity, which was beta plus gamma t, now we know that velocity equals beta plus acceleration times time. So thinking about our definition for acceleration, here's a different way to write it that means the same thing as dv dt, delta v over delta t. It's still the change in the velocity over the change in time. So if that's our equation for acceleration, we can rearrange that to find our equation for velocity, right? Acceleration times time gives us our change in velocity. So if we think about this equation here, v really stands for final velocity, which means this beta is our initial velocity, right? In order to have a change in something, we need both a final and an initial value. So the delta V, the change in velocity, is the final minus initial. So the final equals the initial plus AT. So this equation, now we know both of our kind of span-in variables, beta and gamma, right? So beta is initial velocity, gamma is acceleration. And so our new equation for the position, plugging in those variables that we just found, taking the derivatives, position equals initial velocity times time plus 1/2 acceleration times time squared. And that can also apply to our other equation for velocity, right? Because that has both beta and gamma as well. So we plug those in there. Final velocity equals initial velocity plus acceleration times time. Whew. Those are two very important equations for figuring out the motion of an object, how its position is changing with respect to time, and how its velocity changes with respect to time when there's an acceleration. So these are two of what we call the kinematic equations. And kinematic means describing motion. Now there are quite a few kinematic equations. And so I have them all, well, not all, I have many of them written down here on this slide for you. If you have paper that you take notes with, I definitely recommend writing down these kinematic equations. If you don't already have them memorized from like AP physics or whatever. Um, and I promise physics is more than just a bunch of equations, but these equations are helping us relate concepts together, um, so they are helpful to us. So these equations we've seen before, these ones at the top, we saw these in chapter 2. Average velocity is the change in position over the change in time. Average acceleration is the change in velocity over the change in time. This one we just derived on the last slide. Final velocity equals initial velocity plus acceleration times time. Our change in position is 1/2 initial velocity plus final velocity times time. This one we also derived on the last slide. Change in position equals initial velocity times time plus 1/2 acceleration times time squared. And then here's another one which we haven't derived yet, but that is helpful in many circumstances. Final velocity squared equals initial velocity squared plus 2 times acceleration times the change in position. So this last equation is really helpful when we don't know what the time is, but we do know like how far it's gone, or how fast it's moving. So this one is really helpful for us as well. Now these equations, I have them written a certain way, but they work in both the x direction and the y direction. But we have to treat those two directions separately. Horizontal motion and vertical motion are separate things. They do not influence each other. So we treat them separately. Okay, so we can't put y variables into an x equation. Kendra, will x always mean position? Yes. And specifically, x means horizontal position. So if we're talking about vertical position, like how far something has fallen down, you might see it written as delta y, just to show you that we're talking about the vertical direction. But x or y will always mean position, either horizontally for x or vertically for y. Good question. Okay, now different textbooks will write these variables in slightly different ways. So you might see initial velocity written as VI. You might see it as V naught or V sub zero to show you the velocity at time equals zero. Final velocity, or the velocity at the current moment, you might see it written as VF or just V. It depends on the textbook, it depends on the professor. So try to get used to both of those ways of looking at it. Okay, so I have those equations that we just went through in this little orange box down here in the bottom, just in case you don't have a paper to write them down for reference. But I do want you guys to have a calculator handy because I want you to kind of go through this example with me. Okay, example one, an accelerating car. So a car starts from rest and accelerates at a constant rate of 5 meters per second squared. Part A, what is the velocity of the car after it has traveled 30 meters? Now, a good habit for you to get into when you're doing homework problems or quiz problems, that sort of thing, is to either like circle or underline key bits of information in the problem itself. So, one key bit of information that is very important but is not given to you as a number is this word rest here. So, a car starts from rest. That means that its initial velocity is zero. Right? Our first instinct when we look at problems is often to just like look at all of the numbers. But sometimes professors like to throw in extra numbers just to throw you off, or they like to not even use numbers like from rest. So make sure that you're reading very carefully. Okay. We know it's an acceleration at a constant rate. So that means the whole problem, our acceleration is going to be 5 meters per second squared. And that's positive in this case. If we want to know what the velocity of the car is after it has traveled 30 meters, well, here 30 meters is our displacement or our delta x. I mean, we're going to just assume that it's traveling on a road and not like falling off of a cliff. Well, I suppose it could be. But we'll assume that it's traveling in a horizontal direction. So that would be delta x as our 30 meters. And we're looking for velocity final, right? We know the initial velocity from rest is zero. So we're looking for that final velocity. So what we want to do is choose the equations that we could use for this part of the question. Not all of these equations will be helpful to us. It depends on what we're given and what we're looking for. So we know we want to find an equation that has final velocity in it, because that's what we're actually asked to find. But if we look at the problem, we are not given a time. So any equation that has the variable t is not going to be helpful to us right now because we just don't know that information. So we want to find an equation that has final velocity, initial velocity, acceleration, and change in position. Okay, so final velocity appears in equation 3, equation 4, and equation 6. We're given that change in position, which is appearing in equation 1, 4, 5, and 6. We're given initial velocity, which is in equation 3, 4, 5, and 6. And we're given acceleration, which is in 2, 3, 5, and 6. Now, the only equation that has all of those variables in it is equation 6. Right? You can see equation 4 has some of the variables. Equation 3 has some of them. Equation 5 has some of them. But equation 6 is the only one that has all of those variables. So we'll use that equation. And so here in the equation itself, it has final velocity squared. And so just to kind of shortcut our math a little bit, I took the square root of both sides to get just final velocity. So initial velocity, remember, is 0 because it's from rest. So 0 squared plus 2 times our acceleration times our change in position. That gives us a final velocity of 17.3 meters per second. Woohoo! Okay, part B, how much time has elapsed. Now we are looking for the variable t. So we're going to want an equation that has t in it, along with those other things that we now already know. So we could use any of the equations that involve time. So 3, 4, or 5. Let's just pick the easiest one, and that is equation 3. So our final velocity we just found in part A. Our initial velocity is 0. Our acceleration is again 5. So I took this equation and I rearranged it to solve for t, since that's the variable that we're looking for. So when we do that, we get t equals final velocity minus initial velocity divided by acceleration. And that sort of equation manipulation is basically just algebra, but it's going to be a skill that you need to get good at, so that, when you're taking a quiz and you have an equation sheet, you don't have to write down every way of writing that particular equation. You can just rearrange it however you need to based on what you're given. So anyway, our final velocity is 17.3, initial velocity is 0, acceleration is 5. That gives us a time of 3.46 seconds. So you might notice in these two answers that I'm using 3 significant figures. That's generally a good rule of thumb to follow. Most professors aren't super strict about how many significant digits you use. But 3 is just a good rule of thumb, right? It gives us enough precision without being super overwhelming. Okay, part C, calculate the average velocity. The only choice for this is equation 1. That's the only equation already written out for us that has average velocity in it. So our change in position is 30 meters. Our change in time is 3.46 seconds. Right, we're assuming that the stopwatch starts at 0 and not at something else because we would have been given that information. So that means our time interval is 3.46 seconds. And that gives us an average velocity of 8.67 meters per second. You guys have questions about this example? I know we kind of just like jumped into it real fast, hit the ground running. All right, if you guys do have questions, of course, let me know. We'll definitely do some more examples like this together. No worries. Okay. So related to our motion now we're dealing with motion not horizontally as we were in the last example, but now we're thinking vertically. So the most familiar example of motion with a mostly constant acceleration is what we call free fall. And that's when an object is falling down only due to Earth's gravity. We don't consider things like buoyancy and air resistance and other things like that. We're just considering the force of gravity pulling an object down to the ground. So, a little history lesson. In the 4th century BC, Aristotle thought that heavy objects fall faster than lighter objects, proportionately to their weight. And this just kind of instinctively seems like it would be correct. Like something that's heavier seems like it would fall faster than something lighter, right? No, wrong. This is one of the big misconceptions in motion. 1900 years later, Galileo argued that an object should fall with a constant downward acceleration regardless of the weight if we're ignoring air resistance. And so, um, NASA astronauts, when they went to the moon, they actually did the famous feather and hammer experiment. Because if you think about the environment on the moon, there's no air, so to speak. So there's no air resistance. And so they dropped this hammer and feather at the same time from the same height. Now, if Aristotle were correct, the hammer would have hit the ground first because it's heavier. But actually, they hit the ground at the same time because gravity is the same. The acceleration due to gravity is the same for every single object. It doesn't matter how much it weighs, the acceleration due to gravity is the same when we're um, not considering effects of air resistance, right? So when we're dealing with objects in free fall, that would be objects that are falling or rising, like if we're throwing it up into the air with no outside forces acting on it except for gravity. And of course, since we are on Earth, we do have air resistance. So this is a purely ideal case that we wouldn't really experience in everyday life, but we like ideal cases in physics. So this acceleration due to gravity, we give it the symbol lowercase g. Um, that's how you'll always see it written, lowercase g. And it approximately equals 9.8 meters per second squared, although it is different in different places on the Earth. So here in Melbourne, it was measured to be 9.792 meters per second squared. Higher up on mountains, you'll get a different value than you do like really close to sea level. Also, the Earth isn't a perfect circle sphere. It's, sort of squished because of its rotation. So you're not always at the same distance from the center of the Earth. All of these things make a slight difference for your acceleration due to gravity. But we'll just give it the approximate value of 9.8. On the moon, since the moon has less mass than the Earth does, your acceleration due to gravity is lower, right? That's why you see astronauts like bouncing as they walk along the moon. So its acceleration due to gravity on the moon is 1.6 meters per second squared. Whereas with the sun, since the sun has so much mass, the sun's acceleration due to gravity is 270 meters per second squared. So things would behave very differently on the moon versus the sun versus the Earth. So G is the magnitude of a vector quantity. So that's always positive. But when we're thinking about a scenario, sometimes it's helpful to make down negative. So sometimes you'll see it with that minus in front just to show you that we're talking about the specific direction of down. Okay, and so an object accelerating due to gravity will accelerate at negative 9.8 meters per second squared in the y direction, or 9.8 meters per second squared down. So even though we have a ball traveling upwards, like this soccer ball that's bouncing on the floor, at the beginning it's traveling upwards, but its acceleration is downwards. And so that's why it eventually falls back down again. So let's look at an example in the y direction now. A coin is dropped from the Leaning Tower of Pisa. It starts from rest and falls freely. What is its position and velocity after 1 second, 2 seconds, and 3 seconds? So here's our little picture. Again, I always recommend that you draw a picture of the scenario so that you can get everything straight in your head. Let's think about those key bits of information that were given in the problem. First, it starts from rest. So we're not throwing the coin off the building, it's just dropped. So its starting velocity is 0. It's falling freely, which means we're only taking into account the effects of gravity, not the effects of air resistance or anything like that. We're looking for its position and its final velocity at each of these times. Okay, so we're given time. We're also kind of implied given the acceleration, right? We're on Earth, it's the Leaning Tower of Pisa. So the acceleration of this coin is negative 9.8 meters per second squared, right? Anytime we're on Earth and something is falling, we automatically know the acceleration, negative 9.8 meters per second squared. Great. So I don't have that orange box of equations written for you this time. There just wasn't space on this screen. But if you have them written down, that's super helpful. This is the equation that we're going to use. And this should look very similar to the equation that we used before of x equals initial velocity times time plus 1/2 acceleration times time. Except it has this little additional portion in here, y0. So that's our initial position. Since this coin is not starting on the ground, it has an initial position. Although, what would be most convenient is to set this initial position as the origin of our coordinate system. If we do that, then we don't need to worry about what the height of the Leaning Tower of Pisa is. We'll just say wherever it's dropped from is a position of 0. And as it falls from there, our position changes. So remember, we can establish these coordinate systems to be whatever is most convenient for the scenario. So its position at a certain time equals its initial position of 0 plus its initial y velocity, which is 0 because it's starting from rest. So 0 times time is 0 plus 1/2. The acceleration in the y direction is just the acceleration due to gravity times t squared. So 1/2 of 9.8, or negative 9.8, is negative 4.9 meters per second squared. So this equation simplifies quite a bit to just negative 4.9 t squared. Okay, so that's for its position. We're also asked to find its final velocity. So its final velocity in the y direction equals its initial velocity in the y direction plus its acceleration times time, right? And conceptually, this should make sense because, if we think about however fast it started, and now we're making it accelerate for a certain amount of time, acceleration changes its velocity. So if we think about how long it's been accelerating, plus how fast it was moving initially, that gives us how fast it's moving now. So initially it was moving at a velocity of 0. The acceleration is negative g times the time, however long it's accelerating. And so you see our two equations have become much simpler just based on where we set our coordinate system and the fact that it's falling from rest. Those are very helpful things. So now we can just plug in our values for time, 1 second, 2 seconds, and 3 seconds. So at 1 second, its position is negative 4.9 meters, right? Negative 4.9 times 1 squared is negative 4.9. its velocity at that moment is negative 9.8 times 1, so negative 9.8 meters per second. 2 seconds, we just plug in 2 for t, so we get a position of negative 19.6 meters and a velocity of negative 19.6 meters per second. 3 seconds, we just plug in 3 for t, and so we get a position of negative 44.1 meters and a velocity of negative 29.4 meters per second. Now, we can notice a pattern here if we look very carefully, right? For every 1 second that it's falling, its velocity, well, the magnitude of its velocity has changed by 9.8 meters per second. And that's what acceleration means. It means how much the velocity is changing every second. So the acceleration due to gravity being 9.8 meters per second squared means that every second an object is falling, its velocity is going to change by 9.8 meters per second. Right? And we see that pattern here. From 9.8 to 19.6 is a difference of 9.8. From 19.6 to 29.4 is a difference of 9.8. And we can continue that pattern for as long as the object is falling until it hits the ground. All right, so that's going to wrap it up for today. Do you guys have any questions about those two examples that we went through today? All right, if you guys do have questions, you're welcome to hang out after I stop the recording. But otherwise, we will pick it up here tomorrow with some additional examples of motion in 1 dimension, 2 dimensions, and 3 dimensions. So, launching things off of cliffs and all that fun stuff. That's coming at you tomorrow. So I hope you guys have a great rest of your day, and I will see you then. Bye.